Hey everyone, in this video we're going to talk about the next steps in the air design process, which is the component weight estimation. All right. In this week we will be looking at a series of videos which related to component weight estimation as well as calculating CG and static margin. So this will be one of the most involved process that you go through in the air design, mainly because there are a lot of components on the aircraft and it's very important for us to estimate the weight in a relatively accurate manner, what the weight of those components will be, right? Because again, if you think about it, the entire performance and the cost of the aircraft really depends on the weight itself, right? Yes, there are sophistication that is involved. There is technology advancement. Ultimately, it comes down to weight, right? How much weight you have ultimately depends how much fuel you need to satisfy a certain mission, right? So that's why this is one of the most involved process in the air design process. Okay. Um, and in this video, we're gonna look at the component weight estimation, and the different methods that we're gonna use to estimate the component weight. But before that, we will look at what is called the VN diagram, right? And that will predominantly be the theme of this video, right? Because the results, the outputs from the VN diagram will actually go into the component weight estimation, right? So I think maybe in this video we'll cover the VN diagram, and then the next video we'll look at the component weight estimation, the different methods, right? And the following videos we'll talk about the CG and static margin calculations. So the goals of this exercise are pretty straightforward, right? We want to determine the component weight estimation based on 3 different statistical methods. Because of the variety of aircraft that are available, and because of the variety of methods to estimate the component weights, we cannot just in good conscience just look at one method and go with that. Mainly because the results that you get out of one method may not be completely accurate for the aircraft that you're designing. That's why it's always good to look at different statistical methods put forth by different authors, different engineers, different organizations like USAF, Cessna, things like that, right? So, and then one of the primary process here is the iteration. So you're going to end up calculating a total max takeoff weight for your aircraft, or sorry, the gross takeoff weight for your aircraft, and it won't be the same weight as you started with, in the weight estimation in the constraint analysis, right? So essentially, your wing area, surface area, tail area, fuselage, all of that's going to go through a slight change as you go through the design process or the iteration process, right? Which we will talk about that soon. One of the goals is to also develop a VN diagram and actually calculate static margin and CG. All right. All right. So quick overview of the design process here. You are in the weight buildup and analysis. We're not going to do cost analysis at this point. We will do cost analysis later in the semester. Let's just for now focus on the weight buildup and the CG static margin estimation. Right. So as I said, you're going to end up getting a takeoff weight estimation from the weight buildup. That won't be the same as the weight buildup you got from initial weight estimation, right? So essentially, you're gonna have to go back and calculate the new surface area and new thrust required based on the result from the weight estimation, right? And then put it all through again through the weight component estimation again, and do the iteration until you get a solution which is converged. When I say converged, right, the input to this process should be this relatively the same as the output from the weight estimation. As long as you can ensure that, then you should be good, right? And again, this is very important, so your design will actually go through some slight changes. Okay. So, you're not done with OpenVSP completely yet. You may have to go back and do changes based on what the result, size is going to look like after the estimation. All right. So let's jump straight into the resources that you will need. Right, because there are a lot, again, guys, there are a lot of textbooks out there. I try to see through the textbooks just to get you directly to the sources that you need. So you only need 3 sources for these. The first is the Roscom Part 5, which is essentially component weight estimation. The second is Levi's book, and then Nikolai's book. And then the third is the Raymer's textbook, right? So we're going to rely on all these three resources to estimate the component weight buildup and also create the VN diagram, right? As throughout the series of these videos, I mentioned the chapter and the page numbers where you can immediately go and actually take a look, to get the equations and the relevant steps you need to take to finish the component weight estimation and draw do other things like CG and VN diagram estimations, right? Right. Speaking of VN diagram, let's just let's jump straight into it. Again, this video is primarily going to focus on the VN diagram, all right, and then the next video we'll look at the component weight estimation, right? So before we talk about how we can create the VN diagram for our airplane, let's just first look at what a VN diagram actually is, right? So if you go to any any aircraft, right, if you look at the cockpit, one of the instruments that you see is the airspeed indicator. Airspeed indicator is one of the primary components, components that or primary equipment that needs to go in the flight instruments in the avionics, right? Oh, sorry, not the in the flight instruments. Mainly because everything depends on the airspeed, right? You rely on airspeed for pretty much everything in your in your flight, right? This particular indicator is meant for Cessna 152. What we will do is we'll walk through a little bit about what these colors and the lines represent. All right. So obviously this is a dial going from a speed of 40 knots to like about 200 knots here, right? But there are color codes here as well, which indicate certain things, right? So starting with the lower green dial right here, that essentially represents the 1G stall speed. So 1G in the sense lift equals weight, correct? Lift required to weight to lift, the weight of the aircraft, right? At 1 times the weight of the aircraft. That's essentially the 1G. And the stall speed is a minimum speed you can fly at while sustaining the weight of the aircraft, right? So this condition is purely for power off and flaps up. So if you go below that, you will stall the airplane under this condition. But with the power on and flaps down, you can go much lower. You can go lower than that, right? But this green is for 1G stall speed, all right? So, and then you see this white arc right here. This white arc essentially represents the range at which you can deploy the flaps. Okay, you should not deploy the flaps beyond this white range. Otherwise, you will structurally damage the flaps on the airplane. Okay, so that's essentially this white range. For Cessna, above 85 knots, even above 80 knots, you don't necessarily have should deploy flaps above this airspeed. Okay. On the lower end of the green dial right here is the normal operating speed, right? So this is essentially like a range where you can operate, essentially the cruise speed, or I would say the max cruise speed in here, right? So and then in between, or next or near the max cruise speed, you have the maneuvering speed in here, all right? And this yellow region indicates, a flight speed where you can only go if you have a smooth air, right? If you're entering into turbulence or if there's a particularly gusty day, you should not fly in this region because once again, you may end up overloading the structure, thereby structurally damaging your aircraft, right? And then the red line right here is a never exceed speed. Do not exceed it, otherwise your aircraft will sustainable to damage and it may even break apart. All right. So these are some of the very important flight speeds that any pilot should be aware of, or any designer should be aware of. And because you need to know what are the limits of the aircraft that you're designing, right? And if you have a certain requirements on operating speed, stall speed, maneuvering speed, and all that, you have to make sure the structure, the structure of the aircraft is rigid enough to handle those loads that are associated with the airspeed. All right, that's essentially why we look into what is called this VN diagram, because this velocity essentially translates to the load factor, which is also known as G's that are acting on the airplane. Okay, so here is a typical VN diagram, sometimes also referred to as VG diagram, for a particular aircraft. So all of the dials, all of the speeds in the dials that we talked about in the last slide is actually mentioned here, right? You have the stall speed in point A, right? That is the 1G stall speed. You get the maneuvering speed VA. You get the maximum structural cruise speed. That's the VNL, and then you have the never exceed speed, right? That's VNE. And then here you have a caution range, which is in the ILA region right here, right? So essentially, if you look at this dial, it's really informed by this VN diagram, right? So it's very crucial for anybody operating the airplane, especially the pilot, the co-pilots, and even the designer to know the limits of the aircraft. Okay. So just like we talked about, right, the 1G, 1G is again lift is equal to weight, correct? Right, and then it's the speed you require to sustain the weight of the aircraft is essentially the stall speed, right? Or the minimum speed essentially required to sustain the weight of the aircraft is the stall speed, right? It's a normal stall speed. Now, that stall speed increases as you increase the number of loads. So if you have, if you want to sustain 2 times the weight of the aircraft, then the stall speed increases, right, to about 85, 90 knots in this case, right? As you can see, as the G loading increases, the stall speed also increases. In a way, it's actually a good thing, right? Mainly because, say, consider a case, you're cruising along at a given altitude at a 1G flight, right? Lift is equal to weight, the typical cruise condition. Say you're cruising at a speed of around 90 or 95 knots, right? Suddenly, say you get hit by thermal or like a gust, right? So a gust is essentially a sudden change in angle of attack, right? I mean, there are, airplanes sometimes operate in atmospheric boundary layer. Even if it operates at really high altitudes, there are jet streams, there are crosswinds, and their turbulence, sometimes airplanes goes into the clouds, right, where you have really tumultuous air, really turbulent air. So the gust encounter is unavoidable for an airplane. So that means that say you're cruising along, you enter into a cumulus cloud, and where you have really high turbulent winds. Suddenly, there's a thermal coming, or there's a gust coming perpendicular to the wind, or in any direction that may increase your load factor on the airplane from say 1G to about 3G, say in a worst case scenario. If that happens, you can see that the airplane actually stalls, and that may cause the airplane to pitch nose down, and you'll be able to recover, right? Which is good. Again, it's better to stall the airplane than structurally damage the aircraft, right? Whereas, if you cruise somewhere at a really high velocity, say about 170 knots, right, and you enter into a cloud, or you're doing some sudden maneuver to get to a desired altitude, or go through again array of clouds, right, where you may experience some typical high velocity gusts, right? When that happens, right, you will increase your structural load of the aircraft by a factor of like 4 or 3.5, where you may end up structurally damaging the aircraft, right? So that's really bad. All right. So that's why it's important for any pilot to know, what is the operating limits of the aircraft that he or she is flying, right? So which is exactly why, this point right here is the maneuvering speed of the aircraft, right? So maneuvering speed is essentially the max maneuvering speed right here. You can do all the maneuvers before it, because just in case if anything happens, you will stall the airplane before you structurally damage the aircraft, right? That's the main idea here. So obviously, and again, caution range. So as you increase the airspeed, the gust amplitude kind of increases. That will push more and more towards your structural damage and a structural failure zone, right? So again, I hope you guys understood the concept of VN diagram and why it's important for us to consider the VN diagram. right? I mean, if you want a certain cruise speed, certain maneuvering speed, then you have to make sure that the structure, the airplane structure that you're building, that you're designing, is rigid enough, strong enough to withstand the loads, right? And in order to do that, well, you need to beef up your, structures, beef up your wings, tails, etc., and that will ultimately will add to the weight of the aircraft, which is essentially why we are talking about this in the first place. Okay, so hopefully that makes sense, right? Again, it's not just for stall. Whenever you do a turn, a high velocity turns, at different angles, you will experience different G's, where this VN diagram also comes into play, right? You have to make sure that when you're doing these maneuvers like this, you don't structurally damage the aircraft. All right. All right, guys. So let's. I think even this video may end up going a little longer than I thought. So in the next video, I'll talk about how you can create your own VN diagram for the airplane of that you're designing. All right.